Hi, everybody. Thank you for coming out to Laracon. I want to, first of all, start off by saying that I want to thank Taylor and his crew for inviting me out to speak. I'm really excited and honored to be here, so thank you so much for having me. I also start every talk by putting a link to the slides up. So the slides are already available for you to download. This is especially in case you have trouble seeing something up here. You can go ahead and follow along from your own computer. So first of all, though, I wanted to share a little bit about myself since you and I may not know each other. My name is Ben. I am a software architect for Shootproof, where I work on a platform for professional photographers. We help them manage their studios and sell directly to their clients. So that's what we do. I have been around the PHP community for many years. I'm a co-author of the Zen to PHP 5 certification study guide. That's a little out of date now, I guess, with PHP 7 being out. But it is still a pretty good reference for those of you just kind of interested in learning kind of the ins and outs of PHP, the language. Also, I am one of the original founders of the Atlanta PHP user group, and I currently am an organizer at the Nashville PHP user group. I am the one to blame for putting array column in the PHP core. So that's my tiny little, few line claim to fame. And Sarah Goldman promptly rewrote the entire thing. I am the maintainer and the namesake for the Ramsey UID library. And I am also one of the maintainers of the League, the PHP League OAuth 2 client. Oh, also, I put this slide in here because I always forget to introduce him. This is Rar. He is at Rar the Tiger on Twitter. He is a little guy I take around with me to kind of communicate with my son as I go off on speak at a bunch of conferences. My son is now 9, so this might be one of Rar's last appearances because it might not be getting very cool for him anymore. But I like to take pictures of Rar wherever I go. So if you take any pictures of Rar and you post them on Twitter, mention his name, and that way I can share them with my son. So HTTP, and I'm going to say HTTP a whole lot in this presentation. I hope that I won't stumble too much, and different people have offered different ways of saying it. All of them sound silly to me, like heady or something like that. So I'm just going to try to say HTTP, even though it's a tongue twister. HTTP could be said to be one of the major underpinnings that forms our modern society. I want you to think about that for just a minute. Not only is it a protocol for serving simple web pages, but it's also the communication protocol of choice for serving large applications and for communicating across networks and across industries and across companies. We use this protocol for so many things. It is crucial and critical to our modern society. And despite this talk title, this title is about HTTP 1 just as much as it is about HTTP 2. And so for that, I want to do a little bit of a web history lesson. In 1990, Tim Berners-Lee at CERN in Switzerland created the first World Wide Web server. And from that, he served the first HTML pages, which were just a little bit of SGML kind of used to mark up headers and paragraphs. The version of HTTP that he used back then became known as 0.9, and it was a subset of the 1.0 draft he was working on. It was very simple. It only supported the GET method. And then we moved forward a few years, and HTTP 1.0 continued in draft form, and it was heavily influenced by a man named Roy Fielding, who you might recognize his name from representational state transfer. And it went through the IETF working group under revision after revision to get to a good place for us to all use. It was published in 1996 as RFC 1945. This version expanded the methods and headers that the original version had, but it did not yet support something called the host header, which you're probably familiar with if you've looked at any of the requests and responses in HTTP. But this version didn't support the host header, so it was only able to serve one domain per IP address. In 1997, HTTP 1.1 was released as RFC 2068. That number is a little different because you're probably familiar with RFC 2616 if you keep up with the numbers. Many new headers were added, and then a few more methods. And this is the version number we were using for so many years. But it had a revision a few years later in 1999. This is when RFC 2616 came out. The working group looked at the way HTTP was being used in those early days and decided that some of the methods and headers that they had put in there really weren't used in practice, so they removed them. These were things like the link header, which you might be familiar with from later RFCs where it got reintroduced to HTTP. This is the version that stood frozen in like carbonite for 15 years. And a few little things happened along the way. Like in 2000, we got this upgrading to TLS RFC. And then the years went by. In 2007, something interesting happened. The IETF decided to form a new working group called HTTP BIS. And this working group, I'll come back to it in a few minutes, but it was tasked with revising how HTTP had been used over all those years. A few more things happened. In 2010, we got defining well-known uniform resource identifiers. Use of content disposition header was clarified. We've got some additional status codes. And then in June, 2 years ago, in 2014, HTTP 1.1 was revised and broken apart into 6 different RFCs, 7230 to 7235. And then a year later, we got HTTP 2. So how did we get there? So when I say HTTP is dead, what I really mean is that RFC 2616 is dead. And why is it dead? Why did they do all this revision? What was the impetus? Well, HTTP 1.1 was published in June of 1999. So think about that. The web continued on, and that was like right at the point of the big bubble that was exploding and then eventually burst about a year or two later. But the web just continued to grow. It grew in leaps and bounds. This RFC was 178 pages printed out. So if you ever printed it out, I don't know if anyone's ever wasted trees enough or hated trees enough to print it out, but it was 178 pages. And if you look at other RFCs that the IETF publishes, most of them are usually short, like 20 pages or so. There were a lot of errors in the document. There was a lot of ambiguity, a lot of questions that came up over the years, a lot of misuse of things, just because people didn't know what was intended. And ultimately, the web got bigger than anticipated. They could not foresee how HTTP would end up being used. I mean, think about like the middle part of the last decade, like 2003, 2004, 2005. This is when APIs exploded, and now we had communication over HTTP that was not even previously thought of. Right? We just thought of it as a way to serve pages. Now we're like serving all sorts of requests, and we're driving all sorts of applications just based on this protocol because it's easy to use and it's ubiquitous. So the working group was called HTTP BIS, and they got put together in 2007 to kind of revise all this. The web got bigger than anticipated. Let's take a look at how people are using HTTP and then revise the specs. So bis is the Latin adverb for two, or if you think about it in an adverb form, it's like the HTTP working group Thule, or part 2. When I was in Sao Paulo giving this presentation, apparently bis is a word they use for two, but most Americans don't know what bis means. It was chartered in October 2007 to refine and clarify HTTP. Here's the important part. This is in 2007. They were specifically forbidden from creating a new version of HTTP. So if we look at their charter, that is actually in the original charter. My bold-faced text here says, the working group must not introduce a new version of HTTP. So how did we get to HTTP 2? So what they did produce, though, were these 6 specifications. And the one that most of you would be most concerned with is probably RFC 7231 and then the following. But 7231 is where all the status codes that you're familiar with are defined. All the headers and methods are defined there. But then some of them are broken up, like 403 forbidden. That's put into this authentication RFC. So some of them have been chunked out and put into an RFC where they make the most sense. So 7230 is the new 2616. Let's talk briefly about some of those changes that you can see, some of the refinements. So the first one that I thought was interesting is that user info is now disallowed. User info is that idea that when you had a URL, and if it used like basic authentication, for example, you could put username, :password at domain name, and that could be a URL that logs someone in to a basic authentication site. Well, as you can imagine, that was kind of dangerous because those URLs could be shared and then your credentials were leaked out on the web wherever you shared that. So they decided to get rid of user info. It was just a bad idea. Multi-line headers are now deprecated. This is because this is actually forward thinking to HTTP 2 where you don't need multi-line headers anymore. In HTTP 1, if you've ever looked at headers, some of them can get really long, and so people have taken this practice of dropping it down to the next line, and as long as you have some white space there at the beginning, the server and the client knows how to parse that. Well, specifically, it's deprecated, but in the spec it says that while it's deprecated, they cannot guarantee that a server will know how to parse that, or that a client will know how to parse that. So you're recommended not to use it at all. It's almost completely gone. Browsers used to have a connection limit, or the spec defined a connection limit. That has been removed because, again, this is future-facing to HTTP 2. You don't need that connection limit. The body is now allowed on GET requests. And I think this is kind of interesting because if you had like a really long query string, maybe for search parameters or something, maybe you'd want to have a search body that is a JSON body that you send in a GET request. Well, they now specifically allow that, but they don't define anything around that. So use it at your own risk. That means that, you know, with a GET request, a proxy or intermediary network device, like a proxy, can, or a, what's the word I'm looking for? Edge server can take that request and cache it. They can cache the request, they can cache the response. So for any response that might be, for any request that is the identical request to a previous one that we received, it can just return the cached response instead of going all the way to the origin server. Well, it doesn't know what to do with the body. So that's my point. It doesn't really cache the body. And then expect header is no longer extensible. I don't know if has anyone used the expect header or tried to use it? 100 continue? All right, well, it's not there anymore. It was misused. A couple other things. 201, which is the created response, now allows for multiple items created, so you could send back multiple items, or you could tell the client that multiple things were created, multiple resources. 301 and 302 now may rewrite from post to get. Now, in practice, all browsers were doing this. If you ever, we were using, in practice, we used 301 to mean go here after I've processed something, or 302 to go here after I've processed something. But in reality, the original thinking was that you would say, the location of this resource has moved, send the request that you originally meant to this other place. So no one did that. We were just using it to redirect people to thank you pages after we saved their details, right? So now they've introduced 307, which is temporary redirect, and then 308, which later came, which is permanent redirect. These do mean explicitly, if you send me a post request and I give you this back, you should send that post request to the other location. 400 used to say something about being for syntax errors. They've changed that so that it's just a general bad request response. You could use it anyhow you want. Upgrade required has been added because of HTTP 2. And then 204, 404, these are now explicitly cacheable. People used to cache them anyway, but the spec now says these are cacheable. And then finally, some other things. The location may include relative URIs. So the location header that you used to send back maybe on a 302 response, or maybe on a 201 created response, you'd have a location header with the location of the resource that was created. In practice, we were kind of using relative paths there sometimes, but that was not explicitly allowed. So now it's explicitly allowed. These are the kind of refinements they make for these things. Content MT5 header was removed because no one knew how to use it properly. And then E-tag is defined as applying to the specific representation. And this is why content MD5 was removed. So previously, there was a lot of question about how this E-tag header could be used. Now, an E-tag header is like an identifier for a specific state of a resource. And you would send it in a response so that the next time someone made a request to update that resource, they could use that E-tag value to send it to say if it matches or if it doesn't match this, then do something with the resource. Well, it was very confusing because you might have a JSON response and you might have an XML response. Now, how does the E-tag header work? So now they said E-tag is specific to the representation and not necessarily a unique value across representations. So the other thing that's really cool about what they did with HTTP 1 is within all of these 6 specifications, they've now introduced this idea of registries. So they don't want HTTP 1 or HTTP itself entirely to sit in the dark ages for another 15 years before changes are made. So in order to facilitate change, rather than having to introduce new RFCs that obsolete 7231, for example, now we have registries that allow us to add new headers and new status codes and new methods over time. And we can continue to evolve HTTP to suit our needs. So all of these are here. Again, in the slides that you can download, these are linkable, so you can go check out where all of these are. They all live on the Internet Assigned Names Authority website. But we've got method registry, status code, range units, and so forth. The authentication scheme registrations is kind of cool because now we can register more authentication schemes. One of those that's kind of the newer one is the bearer token that you might have used with OAuth 2. So that's been registered as an authentication scheme, and we have now a way to extend all of that for future purposes. Another interesting one is this forwarded header and the prefer header. Go check those out. I won't go over them here, but they're kind of interesting. The prefer header allows you to say, I prefer a minimal representation of the response. It doesn't define what minimal means, but it allows you to kind of do that in an API sense. So you, instead of getting this huge body back, you might only get these certain little details back. And then I mentioned already the 308 permanent redirect. That's been added as well. To allow you to say, hey, that post request you sent me, I want you to send it here instead. All right, let's talk about HTTP bits a little bit. So we know what they did with HTTP 1. They have split up this massive monolithic RFC into 6 different RFCs. They've revised it, they've clarified it, they've removed things that weren't being used, they've added a few things. And they've paved the way for managing extensions to HTTP. Let's talk a little bit about what happened in the interim years. So in 2007, they're expressly forbidden from creating a new version of HTTP. Well, in 2009, Google did this thing called SPDY, S-P-D-Y. No one knew how big it was going to be, and Google decided to open it up to allow other people to contribute to it. They wanted it to be a community effort, but ultimately it's still owned by Google. And they said, SPDY is going to increase the speed of the web. Now, the problem with that is that because it's a Google thing, Like there's other browsers like Firefox and Safari and Opera. Like, are they gonna adopt this? And if they don't, and I want to deliver a better experience for my users by running Speedy on my server, what do I do with those people, with those browsers? So in 2010, Google released Speedy support in Chrome for all versions of Chrome 6. In 2011, Google continued to innovate on this. They released Speedy across all of their services. So if you were using Chrome, you could take advantage of Speedy immediately. It just automatically upgraded. Then in 2012, something interesting happened. Because of Chrome's adoption rate, everyone else who had huge scale started taking notice. So Twitter deployed their infrastructure using Speedy. Facebook decided to do the same. WordPress.com announced their support for it. And then in late 2012, the IETF working group, HTTP BIS, said, something's going on here. You know that thing we said about not introducing a new version of HTTP 2? Well, maybe there's something going on and we need to take a look at it. So they changed their charter. The first sentence is, the first part is actually really enlightening to what happened. They realized that there was an emerging trend for a protocol that could exist and still rely on the semantics of HTTP while improving the transport. So they decided that it was now part of their charter to create a new version of HTTP. And that very first draft of HTTP 2 was the Speedy draft with basically find and replace, removing SPDY and adding HTTP 2. I'm not even lying about that. That's kind of what happened. And then it went on from there. And now, under the guidance of the IETF and this working group, it was even more open. Other organizations could get involved who were skittish about getting involved earlier when it was a Google project. So that brings us to May 2015, about a year ago, when RFC 7540 was published defining HTTP 2. So why HTTP 2? Well, I've already kind of hit on this a little bit with discussion of what Google was doing, but there were some problems that we face with HTTP today. And the HTTP BIS working group realized, as they saw an increased interest in Speedy and some real-world benchmarks, like Speedy became the testing ground for this new version of HTTP. And because they were shown that this protocol really was making performance improvements, especially for organizations at scale, they decided that we could bring those improvements to the masses, to everyone else using HTTP. So a new TCP binding protocol was possible while still retaining those message semantics we're all familiar with, like the status codes and the headers and the methods. So here's some reasons why they decided that we needed a new protocol. The first is that we were really kind of making inadequate use of TCP. Now there's nothing really wrong with TCP itself. TCP is the transport control protocol, and it's a transmission control protocol, and it is what the internet has been based on for many years. It's what we send all this data across the wire in. It is a protocol that defines how the packets are sent and how they're received. But HTTP traveling over it was an ASCII protocol on top of TCP, and it wasn't very efficient for transporting that data. The other thing that's really, that became very obvious is that over time, the sizes of our web pages have grown, and the sizes of images and other assets have grown tremendously. When we take a look at the trend for some of the most popular sites on the web today and what it takes to download their front pages, a clear pattern emerges. Over the years, the amount of data that needs to be retrieved has gradually risen up to and above 2.1 megabytes per page load. And what's more important is that we're averaging well over 100 objects requested per page load. And so when you load a page, it's not just one request, right? It's all of the assets that page requires to make itself visible to the user. That includes the style sheets, the JavaScript, all the images. All of these things have to go into that one page load. And so now we've got things where we've got like well over 100 objects being requested. And I mentioned earlier that the browsers have a connection limit. And so that means you got to get creative. I'll talk a little bit more about that in a few minutes, around how you deliver those assets. And this is only going to increase as we build more complex and rich web applications. And the reason for that is in our organizations, we take a look at what people are using to browse the web, whether it's a smartphone with LTE connection or a home with a high-speed internet. And we make the decision that, okay, most people are going to be able to download this fast. And so we'll go ahead and use the larger images or the fancier assets. And the problem, though, is that while bandwidth has increased, latency has not gotten better. So there's not been an improvement in reducing latency. And so the server round-trip time has kind of roughly just leveled out. We're not getting faster connections to the server. And while HTTP pipelining exists, and I'll talk a little bit more about that in a minute, most have it turned off because it has its own problems. And so the browsers themselves ship with that feature turned off. So HTTP 2 is able to get around some of those latency issues and provide faster connections. Another thing, I just mentioned HTTP pipelining problems. In Daniel Stenberg's book, HTTP 2 Explained, he describes HTTP pipelining like waiting in line at a bank or the supermarket. So you just don't know if the person in front of you is going to be fast or slow, or they're going to be that annoying one that just takes forever and they want to get out their wallet and just count things out, and you're just standing there like, I've only got 2 items, just let me go. This is called head-of-line blocking. And I have a short video by Ferdinand Lutz called Stay in Queue that I think illustrates head-of-line blocking perfectly. So there's no great solution for this. And even today, a lot of browsers have this feature turned off by default because of the head-of-line blocking. So as web developers, we've learned to deal with these issues, and we've written at length books and articles and blog posts, and we've developed training material and courses. We've created an entire industry around solving just these problems. Because most of the problem is in making the amount of requests we make. That's what slows down a page load. So we've decided that if we can reduce the number of requests that are made to the server, then we can speed up the apparent page load time for the end user. So here's some ways we've dealt with that. Spriting, because it's better to send one really big image over HTTP than like thousands of small images. Because those thousands of small images make thousands of requests, and that bogs down the request time or the load time of the page. The problem, though, is if you need to change like this little tiny image in here, you can't even see my pointer, like this little image, it invalidates the entire image. You have to bust the cache for everything when you change one image. Another way we've solved this is inlining. So instead of actually sending a request for an image, let's inline that image into the image source. We can do this with SVGs, we can do this with CSS, we can do this with actual just base64 encoded data like you see here. This is a GIF that's base64 encoded, and it's a folder icon. Better to send it like this than to have a bunch of different requests for it. Another thing is concatenation and minification. So we've taken all of our JavaScript, we have all these different files that helps us organize our project, that helps us keep things separate and neat and clean, and then when we go to deploy it, we want to just put it all together, jumbled up, remove all the spaces, and send that out. Because again, it's better to send one request and get one response than to send a whole bunch of different requests for all the individual library files. Again, the problem here, though, is that you might not need all those files. One page might only need a function that exists in this, and you're sending all of your functions to the front end. And so we've gotten creative with that as well. We might minify or concatenate smaller files based on the functionality that a page needs. But again, we're just compounding the same problems on top of each other, using this to solve this bigger HTTP problem. Domain sharding is another way to do this. So again, there was a connection limit in the browser, and while HTTP kind of specified 2, browsers in practice were really, it was up to the browser how they wanted to do the connection limit, but they were usually doing like 6 connections per domain or something like that. And that means you can only have that many requests per domain. So if you've got 100 assets to deliver, and only 6 requests per domain can be made, well, how do you deliver all of those assets quicker to the browser? One way is to use multiple different domains. That way, the browser, you get around that connection limit. The browser will open up more connections to more domains, and you can deliver all those assets at one time. And that's what we do with domain sharding. So HTTP 2 attempts to fix these problems. It does this in a variety of ways. The first is a binary protocol. Now your first reaction, because I mentioned earlier that HTTP 1 is an ASCII protocol over TCP. This is a binary protocol over TCP. And your first reaction is, oh, well, now I can't inspect it anymore. I can't open up, I don't know if anyone of you ever does this anymore, but I can't open up Telnet and just type in an HTTP request and get back the response, because it's all binary. I have to type 0s and 1s now. But it's a better protocol over TCP, and newer tools will be available. Already, things like Wireshark have the ability to inspect that network traffic and break up HTTP 2 into a representation that you can read. And curl already has HTTP 2 support involved in it. So over the binary protocol, we're now chunking HTTP up into frames. And these frames are binary frames, and they're kind of organized a little bit like this. And the reason they're set up in these frames is it's easier using using a binary protocol to kind of find the beginning and end of a frame. We don't have to like count characters or spaces. We know exactly where things fall within that frame, especially when we lay it out like this. So you've got a header on every frame, and then a body on every frame. And this is, the frame payload is where the body goes. And then you've got this 9-octet header with information like length, type, flags, the stream identifier. And then we've got multiple types of frames that you can send. So the ones that we're most familiar with are where the data goes that we're familiar with, like headers and the body, like HTML. Those are in the data frame and the headers frame. But there's other frames, like a priority frame, a promise frame. I'll talk a little bit more about the promise frame in a few minutes. There's a settings frame and so forth. The other benefit to HTTP 2 is the idea of multiplexing the streams. So only one connection is needed to the domain. You don't need multiple connections. And all the data can be sent across this one connection, and we don't have head-of-line blocking anymore because the frames are able to be interleaved together. Order matters, but when they're interleaved together, they specify their order so that when they get to the endpoint, whether it's the client or the server, they're able to take them apart and reassemble them back to where they need to be. So that looks a little bit like this. So imagine, and this came again from Daniel Stenberg's book. I think it's a really good way of illustrating this. You got two different toy trains, right? They're connected with magnets, or that one's connected with just little holes with the pegs. They're different. Each one specifies something different. But if we want to send them all together over HTTP2, we can do that by putting them together like this. And then when they get to the receiving end, it's able to break them back apart to look like this. It knows exactly what pieces belong to which stream and which frame. One of the ways it does this is through priorities and dependencies. So streams can have priorities set on them. For example, a client could use this to specify which streams are more important, and it can tell the server that a stream is dependent upon another. This allows a browser to do cool things, like when you're switching tabs, it can immediately set priority to the new tabs, to requests being made from the new tab. Or if you're scrolling down a page and the client knows that certain images are higher up on the page than others, it can set priority for those higher images to be loaded faster or first, or requested first and responded first over the images further down on the page. Another thing that HTTP2 takes advantage of is header compression. Now, HTTP2 itself doesn't define a header compression method. They allowed that to be another RFC called HPAC, and that also allows the ability to extend header compression, to have different forms of header compression. But the thing is, headers, from request to request on your own sites are very similar, and they take up a lot of space, especially if you're using the same headers over and over. So you're using a lot of bandwidth just by sending these same headers over and over. Well, with HTTP2, you can set a header as being relative to a certain stream and kind of reuse the same stuff over and over. And that way, you don't have to eat up all your bandwidth by using, by sending the same headers multiple times. And lastly, another really big benefit to HTTP2, and the thing that I'm going to talk a little bit more about in a minute, is server push. This is the idea that the server can decide, hey, I'm going to go ahead. I've received one request from this client, but I also know that that request is usually followed by all these other assets, these images, these style sheets, these JavaScripts. I'm going to go ahead and send them all to the client. And the client can also see all of that coming in and decide whether or not to tell the server to stop sending them. So it can get efficient on both sides. So the client can say, I've already got those, or I don't really want those. I'm going to stop you right now, and it instantly stops it. Right now, we kind of try to do that a little bit. Like if you close a tab, for example, and something was still loading, it's unclear whether that would instantly stop the communication or whether it's going to try to finish. Now with HTTP2, the client can actually tell the server, stop, and it stops. So great. How does that affect me? Because all of this stuff sounds like it's really low level and under the hood. Well, it is mostly seamless for web developers. A lot of this stuff is stuff that's the client and the server are going to be concerned with, and you're not going to have to do anything about. But there are some ways that we might develop applications differently as a result of HTTP2. One is no more image sprites, right? I mentioned that that was a way to get around the connection limit. The whole idea of all of these optimizations that we've built up an industry around in HTTP1 is to get away from making all these requests to the server. If we don't have to limit the amount of requests we make because we have an efficient and optimized protocol for making as many requests as we want to make, then there's a lot of things that we do right now that we no longer have to do. And in fact, if we can get back to some better principles of, I only need these images when I need them, or I only need this JavaScript when I need it, or these styles when I need them, then we can deliver only the things that are needed to render the page instead of delivering all of those things at one time. Domain sharding might actually hurt your performance because now it has to open multiple connections to each different domain. That's because streams, or one connection serves one domain, and if you're trying to serve images from a different domain, it's going to have to open a different connection. Now, there is something that is in the works right now, a proposal to try to allow HTTP2 connections to serve multiple domains. I don't know exactly where that stands. There are security implications involved in that, probably some cross-origin type stuff that they'll have to work out. But that would allow you to use the same connection to deliver multiple images or multiple assets or resources from various different domains that you control. So awesome. Those are things we don't need anymore in HTTP2, so I'm going to go do all that right now. Well, maybe not so fast. Hold your horses. We're still in an HTTP1 world. But people are catching up. So according to W3 Techs, as of right now, 8.8% of the top 10 million websites in the world support HTTP2. And this is a recent screenshot from caniuse.com, which says that this is showing browser support. Most of the common browsers these days support HTTP2. Some outliers are things like Safari and IE11 are not quite there. There's some support. And Opera Mini, I don't know if anyone's using that unless you're using a Nintendo Wii. I think that was an Opera Mini, right? But everything else that people are using in practice these days has almost 100% support for HTTP2. This is good news for us. But obviously, in order to support HTTP2, it's not just a browser you need, it's also the server. You can't serve requests over HTTP2 unless you have a server that supports it. So as of these versions of Apache, Nginx, and IIS, they have full support for HTTP2. You have to go in and configure it and turn it on and that sort of thing, but they do support it. There might be a few outlying things to do with server push that they don't fully support yet, but I do want to talk a little bit about server push. So what can I do now? The thing you can do now, if you are using an HTTP2 server, and if you're serving to people who are using browsers who understand HTTP2, and most of your users probably are using a browser that supports HTTP2, and this is because all of Google's stuff is being served over it, all of Facebook's stuff is being served over it, all of Twitter's stuff is being served over it. These big players are all using HTTP2, which has been driving the adoption rate for the browsers and for servers. You can do server push from your own websites. So it's very easy, first of all, to tell if you're serving requests over HTTP2 using Firefox's Web Developer Network Inspector. So if you use that network inspector and you open it up, you'll see a version header, it looks like a header, that says HTTP2. And this is actually not a header coming from the server. And then they'll add this other thing that says X Firefox Speedy, which is not coming from your server either, but Firefox adds it in there and it says H2. This is a clear indicator to you that you are serving this request over HTTP2. Now, so that was a request over HTTP2. We'll look at it a little bit more detail in a minute. But let's compare that to an HTTP1 request. So here we have a HTTP1 request, and we've got the network inspector open. There's not a lot special going on here, and I don't have a whole lot of assets. But as you can imagine, in this typical kind of a web request, if I had a lot of images on this page, you'd see this bar at the bottom fill up with all of the requests that my browser is making to fetch all of those images, all of those style sheets, all of the JavaScript, and so forth. This one, though, is not a very big request. So you see that it finishes pretty quickly, but you can kind of see over here out to the right the milliseconds it takes to make each of these requests. Now, if I'm looking at the same thing with HTTP2, this request is being served over HTTP2. It looks very similar, right? This is without server push. The requests look almost the same. We're taking advantage of the binary protocol here, but there's not a lot of difference in how it got served. The client is still making each of these individual requests. But using PHP, we can invoke server push on the server to send these requests ahead of time. So with server push, this looks a little bit weird because I think the network inspector gets confused here of what's going on. But you see over here on the right, like almost all the requests look like they went away. That's because they were all served back within this first request. So the client already has them. And instead of, I mean, it looks like it got them, but instead of making the request to get them, it just serves them from its cache. So we can actually see that a little clearer. This is hard to see on the screen with a tool called NGHTTP2 or NGHTTP. It is a command line tool that allows you to make an HTTP2 request and then see all the frames that are coming back from the server. And in this case, at the very bottom, you can see the headers frame right here. These are all priority frames. Here's the settings frames. The headers frame looks familiar. You've got method get, path, slash, scheme, authority, accept encoding, user agent, and so forth. Here is where the magic is happening. These are promise frames, push promises. And what this is telling me is that when I made that one request to get the home page, the server went ahead and pushed all these to me. And you can see their paths. So like CSS, bootstrap theme, CSS, bootstrap CSS, and so forth. So how does that work? Well, if we go back and we look at the network inspector again, you'll see this link header. And in this link header is where this is happening. Now the client is not using this link header. The browser does not use this link header. Browsers can use link headers, but in this case, the browser's getting it, but it does nothing with this link relationship that I'm about to talk about. It's all on the server side. The link relationship is the preload link relationship. This is in draft format, but it's gaining adoption. It provides support at the server level for telling a server that there are other things to send along with this response. So here's what it looks like. So you're familiar with setting headers in your application. You set a link header, and then you give it a path to whatever asset it is that you want to deliver, that you want to push. Then you define the relationship as preload, and then there's this little indicator that kind of indicates to the server what that is. Whether it's you can say style, image, script, and so forth. And so you're able to set this, and this indicates to the server, Apache is what I used in my tests. It indicates to Apache or Nginx that you want these to go along as well. And so in your application, what you might want to do, if you're going to try to implement this, is you want to first check to see if the request is being made over HTTP2. If it's not, you can still set the link header, and nothing will really happen with it. It'll just go to the client. But if the request is being made over HTTP2, then the server will make use of this. So you can check if the request is over HTTP2 from your application by using the server protocol superglobal variable or server variable. And it's just going to have the value HTTP/2. If you're over HTTP1, it'll say HTTP/1.1. And to set those link headers, all you have to do is use whatever response object you're using, or you can use the header method function directly in PHP to set the link header, and then the value of it. And in this case, I'm setting a whole bunch of them, as you can see. Also, the third parameter in this case is really crucial. The third parameter is false. And what false does is it tells PHP not to clobber previously set link headers. So the normal function of this is it would end up, if this was left out, it defaults to true. This is the only link header that would be sent, the last one set. So you want to turn on, you want it to say false so that all the link headers are set. And so now you have server push. That, if you're using HTTP 2 server, that'll tell your server to go ahead and set up a push promise to send all of these items to the client, and the client will receive them, and you can set cache headers on those things, and so the next time the client needs to get that asset, it already has it, it's already in its cache, and it's not going to make another request back to the server to get it. So for now, we're still in an HTTP 1 world, but there are a few things you can do if you're already on an HTTP 2 server to go ahead and prepare for that massive change. I think in the next few years, almost everyone will be running HTTP 2, and you can do server push now. But continue, don't go tell your team that I told you that Ben Ramsey said get rid of sprites, or that Ben Ramsey said we're not minifying anymore. Because those are still techniques that you probably need to do right now until the rest of the world has kind of rolled over and gained adoption of HTTP 2. So HTTP is dead. Long live HTTP 2. And I think I have a few minutes for some questions. So if anyone has any questions, I'll see if I can see anything. Yes. Okay, do I know of any PHP libraries that help facilitate making requests in HTTP 2, right? Oh, the server push, creating the server push. I don't know of any. As I was pointing out here, it's really just the matter of setting a link header. I'm sure that you could create a small, simple library that would help just kind of say, here are my assets that I need to send link headers as, and it would add them. I don't know of any off the top of my head, but it seems like an interesting thing to create. What? You can do it in middleware. In Laravel already? They already have the... Oh, I know they have middleware, but is there like a specific server push one? Okay, not yet. I do know that the curl library in PHP, I believe, might already have support for making HTTP 2 requests. If not, it's in the works. Anything else? All right, thank you very much.